if you can show you've got Dulwich University, we will be giving you more money.
That's Teams. Oh, correct, we've got Teams up on display. That's fun. Whoops. Right, share screen. We'll just share screen. I'm not putting anything discriminating to hide. There we go. Lovely. Fabulous. Let's see. Yeah. I'm happy. Sorry, you may or may not be able to hear me. Is currently for attendance. If you filled it out last week, you don't need to, but please feel free. I'm so sorry for your loss. So, PowerPoint time. Sent. Please. Ah, okay, that works. Good. I have that on this screen. Ah, brilliant. I can see everything now. This is good. People online, can I get a thumbs up if you can hear me? Anything at all will be great. Yes, you can. Fantastic. Okay, now that I've checked, the lovely people online can hear me. I'm sorry you're going to get the side of my head, making do with my laptop camera. Thank you all for coming, giving up your time on a Thursday afternoon / evening when I'm sure you can think of far better things to be doing, or at least more exciting. You've come to a lecture on plasma physics. Hooray! Just a very quick show of hands. Who knows anything about plasma physics? More than I thought I was going to get, I'll be honest. Great. So the very first thing that I would like to do is ask the question, what is a plasma? And I have a Menti for you all to have a go at. once I've figured out how to switch my screens. So present that. How do I stop? Is that working? Huzzah, it is. Oh, that's not the right question. Hold on. Plasma. So this is a word cloud activity. Anything that comes to mind when you think of plasmas. It could be examples of plasmas. It could be defining features of plasmas. Show me what you do or do not know. It's perfectly fine to know nothing for the sake of this. I'm just trying to find a benchmark of where we're at. To be fair, a soup of ions is a very good description in all fairness. I got more people joining the lobby. I do. Oops. Yeah, so we're starting to get a vibe here. Ions, energy, heated. Someone's put matter. It is matter. It is a state of matter. It moves every time I try and read it. Stars are indeed made of plasma. One of the 5 states of matter. Are there 5? There's definitely 4. What's the 5th? I'm gonna have to Google this myself. Yes. Oh, yeah, I should have known that one. I am a physicist by trade. I just stopped doing physics to do an engineering PhD. So to give my ignorance of current physics, plasma is love. Plasma is life. No, I'm kidding. Yeah, okay. So we've got the general vibe. We like blob, do we? Blob's a bit vague. Deprived of electrons. A decomplatro, it is. That's true. Great. A soup of ions. It's hot. It has a lot of energy. Right. So I'm going to stop you from doing that. I mean, you can keep going if you want, but I'm going to carry on with the lecture. Hopefully, please work. Yay! Right. So here's today's lecture. My name is Charlotte. What is plasma? We've done that. So today's learning objectives. I know this is very formal, but it's good for you, I swear, to know what you're going to learn before you do. So by the end of this lecture, you should be able to click on to the next slide. Recall the defining features of the plasma. Be able to describe the motion of charged particles in electromagnetic fields. So those of you with a physics background should find that easy to start with and gets progressively harder. And applying knowledge of particle drifts to discuss confinement techniques, which is where we start applying to fusion. So, what are the defining features of a plasma? There are 4 of them. Before an ionized gas is considered a plasma. So you're all right, plasma is made of ions. People tend to describe it as an ionized gas, but not all ionized gases are plasmas. So a plasma has to satisfy quasi-neutrality. So it's neutral overall, but not all the time. It's able to shield and apply electric field. It must behave like a fluid, as described by magnetohydrodynamics, or just MHD if you don't want to have to say it every time, because it is a long word with a lot of syllables. And last but not least, it must have a large number of particles in the shielded region, which is called the Debye sphere. If none of this makes sense, that is fine. What I'm going to talk about today is largely quasi-neutrality, shielding electric fields. I am not touching magnetohydrodynamics today. That is more advanced plasma physics, which requires a lot more maths I personally don't want to touch right now. And considering some of you will never have seen this stuff before, I don't want to scare you. And large number of particles in the Debye sphere ties into the shielding, so you'll kind of get 2 for 1 there. But this is like the textbook definition. So, ionization. We all know plasmas are made of ions. However, a plasma does not have to be completely ionized. There must be enough charged particles so that the other plasma conditions I've just shown you are met, but they don't all have to be. You can have neutral particles in your plasma, and that's fine. Ionization is dependent on temperature and is represented by the Saha-Langmuir equation. Brace yourselves. Looks like that. Not the friendliest. Kind of the interesting bits that you should pay attention to. That represents the number density of the rth ionization state. So if I'm looking for the first ionization state, that just means how many of my ions have had 1 electron removed. If I was looking for the 5th ionization state, it would be how many have had 5 electrons removed, and so on and so on. That is the Debye wavelength for thermal electrons. I've never had an agreement on how to say that name. I believe it's Dutch. Feel free to disagree with me, or if anyone is Dutch, educate me, please, I beg you. It's dependent on temperature, but you don't need to know the details unless you're super interested. And these lovely things over here are the ionization energies of the ionization states. So if you wanted to work out how many of your ions are ions, this is how you do it with some not very pretty maths. Let's admit some more people into the lobby. There we go. However, that's kind of gross, and I don't like doing gross maths because I'm an engineer now. I like numbers that I can put into calculators and out comes the answer. Well, I've gone too far. There we go. Hydrogen only has one ionization state because it only has one electron. This is good news for us because it means we can get rid of so much of that maths and simplify it to this, which is now the ratio of ions to neutral particles. And hopefully you can see the temperature dependence a bit more clearly. It's largely a temperature to the power of 3/2 times an exponential with an energy power. If you do thermodynamics, that sort of format of equation should be familiar to you. If you don't do thermodynamics, don't worry about it. So what does this sort of function look like? For a typical fusion plasma with a number density of electrons or ions of 10 to the 20 per meter cubed, this function looks like this. So the probability of being an ion is on the y-axis and temperature is on the x. So hopefully it shouldn't be too groundbreaking that as I increase my temperature, the likelihood of something becoming an ion increases because now the electrons have enough energy to escape the atom and you get an ion as a result. One thing you may have noticed, oh yeah, all ions are effectively ionized at about 1.5 eV for a 10 to the 20 plasma. However, that likely doesn't make sense to you because plasma physicists are weird. They don't use Kelvin, they use electron volts. What does that mean? Electron volts are a unit of energy, and the logic is the energy for a gas or a plasma is usually about kVt. I've taken some gross oversimplifications there. Feel free to argue with me about real gases and the like. For this, kVt. We use EV instead of Kelvin. This is how you convert. This may be useful to you if you want to read papers about plasma physics and they start talking about, oh yes, I have 2 EVs. What does it mean? This is how you convert. So your temperature in electron volts is equal to Boltzmann's constant times the temperature in Kelvin divided by the elementary charge. It's not that nasty to convert. You just have to get used to it. Or in other words, 1 EV equals 8.62 times 10 to the minus 5 times 1 Kelvin. If you just want to put a number in a calculator like me, because I'm lazy. More realistically, 1 electron volt is about 10 to the 4 Kelvin. That's normally the number you're going to be interested in, which means 1.5 EV is about 15,000 Kelvin. So nice and toasty. Anyone want to take a guess about how hot fusion plasmas normally are? It is totally fine if you're completely off the mark. Go on. 1,000,000 Kelvin. Not quite. Normally, no, sorry, it's about that actually. 10 keV. So 10 times 1,000 electron volts, which is a big number. Fusion plasmas are stupid crazy, but effectively for fusion plasmas, they're always ionized. We don't have very many neutral particles in them unless we put them in. Yeah, that's the point I'm trying to make here. So that's ionization. Now we get to talk about bi-shielding. This is where it gets juicy. So I have shamelessly stolen this picture from a chemistry textbook. This is an electrolysis diagram. Hopefully at some point in your scientific lives, you'll have come across electrolysis. If you haven't, it's effectively the process of you stick 2 electrodes in normally a fluid and you separate out the ions based on their charges by applying an electric field. Because a plasma is effectively just a soup of ions, we can do the same thing, or at least we can think of it in a similar way. We don't literally stick rods in plasma, they would melt. But when we apply an external electric field, the ions are attracted to the opposite charge. So positives go to negatives, negatives go to positive. And this buildup of charge cancels out the external electric field you will have applied by creating its own electric field. So really high-tech diagram. Ta-da! Yeah, so all my positive ions have moved to my negative electrode, all my negative ions have moved to my positive electrode, and in the middle, we have a region where the ions no longer feel an electric field because it's cancelled out by the electric field I've induced by having the charges move. In theory. This does not work in practice. Debye shielding is not perfect because ions have thermal energy, and if something has thermal energy, it is perfectly possible for it to have enough energy to overcome the electric potential that exists. This basically means instead of getting a nice clean cut-off, we have a bit of a smearing of the electric potential, which is what you can see on this plot here. And the layer of this shielding, or the layer thickness, is known as the Debye length. So the Debye length is effectively how long in physical space is it before the edge of your plasma, which is experiencing, say, a positive electric field, stops experiencing an electric field as you go further and further into the plasma. Oh yes, KBT equals your electric potential. If they're about the same, your ions can jump in and out as they please. Yeah, so the definition or the defining part of the plasma that's useful here is the length scale of the plasma must be much bigger than the Debye length, because if you have a really huge Debye length or a really, really tiny plasma, it's not neutral on the inside anymore. It will experience an electric field the whole way through, which is not what a plasma does. This maintains quasi-neutrality in the bulk plasma. So that's where that comes from. It's a tiny feature. I should have kept my book earlier. But yeah, that's Debye shielding and how it ties to quasi-neutrality. The reason why it's called quasi-neutral is because the outsides are not neutral, they are charged, but the interesting bits on the inside, which is neutral overall. So that's the idea. Does anybody have any questions they want to raise now? It's totally fine if you don't. I will check online as well. You should have access to a chat, people online, but if you don't, stick your hand up and we can unmute. Great, okay. So that's your defining conditions of plasmas. Next up, charged particles and electromagnetic fields. How exciting. So for some of you, this will be old news, but it may not be for all of you. But the electric force acts along electric field lines. So any of these pictures you see with arrows on, positive particles move along the field lines, and the force is equal to the charge times the electric field strength. Magnetic forces are not as friendly. They act perpendicular to their field lines, which is where you get this lovely cross product from. So those of you that work with vectors should be familiar with cross products. If you're not familiar with vectors, that's okay. You're probably not going to need to do any maths with them. You just need to know they exist. And for you, this diagram is very useful, shamelessly taken from BBC Bite Size, because it's actually quite helpful. I still use this in my day-to-day because I can never do it in my head. So the way you work out the direction that the magnetic force acts in is you get your left hand and you make physics gang signs. Your thumb represents the direction the force is going to point. Your first finger is the direction the magnetic field is pointing in, so the arrows on the page, and your middle finger represents the current. When we say current, we mean the direction a positive charge would be traveling in. Please don't argue with me about how current is actually made up of electrons. I know it's backwards. I don't make the rules. You just got to live with it. But this is the technique we use to work out directions of forces. So, quick quiz. Another Menti activity for you. It should be exactly the same Menti. So if you've still got it up, you'll be doing well. I've got to click on to the next slide though. And close PowerPoint, hopefully. Please work. Or can I just share the window, maybe? Share this window. Share. Oh, that's working. It's not working. Silly thing. I think it's working for people online. Okay, there we go. It's the wrong question again. Why is it? Right, we'll try again. Okay, it's decided it wants to skip the middle ones. Bear with me for a second. Oh, that's why it's skipping the question, because the questions are in the wrong order. That's not helpful. Okay, so a stationary positive charge is in a uniform electric field, helpfully represented by this diagram. It's very high tech, I know. Which direction is it going to move in? Yeah, so this one seems to be quite a consensus. It is going to move to the right. It's an electric field and it's a positive charge, so it just follows the arrow. It's really easy. We love this one. If it was an electron, it would move the other way because it's dependent on charge, and electrons don't follow the arrow directly. They go in exactly the opposite direction. So your next question, a moving positive charge enters an electric field. How does it move? Yeah, okay, I get the idea. We can do electric fields. This is good. Yeah, again, it's going to follow the arrows. It's going to enter the field and then turn, so it's traveling down the page. Very nice. Okay, where's my next question? Right, stationary positive charge in a B field. This is magnetic fields now. Which way is it moving? All right, I didn't get you. I tried. Yeah, if it's not moving, there is no magnetic force. You have to have a moving charge in order for it to care about magnetic fields. So this one stays still. Sorry, I can't let people in. I'll have to wait. Right. Moving positive charge entering a B field. How's it moving? Okay, well, good news is you didn't put up or down. I like that. In this case, if I've done my maths right, it is into the page. This is prime example of physics gang signs. The idea is you get your left hand, because you're interested in the force to tell you where it's going to go. First finger points down the page in terms of your magnetic field lines, and then your third finger is going to point that way as you see it, and then thumbs point towards me, so into the page. For people online, you can imagine me doing that. Right, last one. Moving positive charge enters a B field. How does it move? Yeah, didn't get you again. I'm disappointed by this. I thought this was going to be a real teaching moment, but you know it already. If I am traveling in the same direction as my magnetic field, I will not experience a force because I'm not traveling perpendicular to the field, and the cross product says you have to be perpendicular or have a perpendicular component to care. So congratulations, you know your basic electromagnetism, forces on charged particles, all that jazz. I'm very impressed, mainly because I no longer have to worry about teaching you that. So where were we? Quiz. Okay, yes, people online, I'll let you in. Where are we? People letting in. There we go. Right, so this is now continuing on. So in general, charged particles in uniform fields. These are the easy cases. So hold on to your hats. Particles that travel perpendicular to a magnetic field travel in circles around field lines. In general, the magnetic force acts as a centrifugal force. If you don't know what that is, don't worry, it goes in circles, like this lovely diagram shows. And the frequency at which it goes around these circles is known as either the gyro frequency, the llama frequency, or cyclotron frequency. Take your pick, they're all the same thing, just named different things. And that is equal to the charge of your particle times the strength of the magnetic field divided by the mass of your particle. It's not that terrible to derive that equation if you're interested. I think it's just above an A-level physics paper standard. I can't see the slides online. Thank you for telling me. I'm sharing the wrong window, that's why. No, I know exactly why. It's because I changed which screen I was sharing. But thank you for shouting, whoever it was. But yeah, now you can see the slide about charged particles going in circles for your reference. So continuing on. There we go. If we introduce an electric field perpendicular to the magnetic field, so in the direction of the red arrow on your screen, we get helical motion, so like a corkscrew this time. So we still get the circle, but now the circle is moving in space. And this is known as the guiding center of the oscillation is drifting. The guiding center is just the center of that circle. So in our case, it's drifting kind of to the right and out of the page. This particular drift is known as E cross B, because the way you work it out is by taking the cross product between your electric and magnetic fields and dividing it by the magnitude of the magnetic field squared, if you are particularly interested in doing that. But what if the electric field is time dependent? So I start off by applying an electric field to an ion that is stationary. That ion is going to start accelerating, in our case to the right, and it's going to get faster. But as the ion's velocity increases, it's going to experience the magnetic force because there is also a magnetic field in existence here. Because it experiences the magnetic force as well, we get E cross B drift. In this case, it's acting down the page. For those of you that may be confused by notation, the little kind of circle with a dot next to the B means that the magnetic field is coming out of the page. Its counterpart is a circle with a cross in it, which means it's going into the page. The easiest way to visualize it is if you were firing an arrow with a bow and arrow. If the arrow was coming towards you, you'd see a little pointy bit. And if it was going away from you, you would see the crosses of the feathers on the end. I really hope you've never had to see the end of an arrow that way, but it's not fun. But regardless, we get this E cross B drift and we start heading down the page. But because it didn't start immediately, we have shifted some way to the right before we started drifting downwards, helpfully labeled as shift. It starts to gyrate and E cross B drift occurs. Note it is shifted slightly in the X direction. So if I now turn off my electric field and then turn it on again but in the other direction, I get something like this. Now it goes in a circle. It does the same thing, but backwards. Direction of drift is reversed, and you can see that I've shifted in the X direction again, but this time to the left to kind of end up back where I started. This is called polarization drift. And polarization velocity, which is the equation you can see there, is easiest to think about as how far have I shifted and how quickly did I do that shifting. That is the simplest way, or you can do the vector calculus. Yay! I personally don't want to do the vector calculus, so better you than me. Note that this does depend on mass through the gyro frequency, which means that ions will have a much greater polarization velocity than electrons, which means they start splitting apart, and that's why it's called polarization drift, because your ions and your electrons no longer hang around in the same soupy area, they kind of move to separate sides. Anybody wanting to pull the emergency stop right now? Please say something, because it's not the easiest, and I appreciate that. Just going to check online as well. Oh, I have someone in the chat. Is that the message about not being able to see the screen? Oh, okay, yeah, fab. Great. So next up, which I'm sure you're going to love, once I can click on the next slide, there we go, inhomogeneous B fields, because homogeneous wasn't fun enough. So we are going to ignore electric fields for the time being, because this is hard enough as it is. If the magnetic field varies in space, then the radius of the oscillation of your particle is also going to vary. If you have a stronger magnetic field, you get a smaller radius of oscillation, and if you have a weaker magnetic field, you get a nice big circle instead. So what this diagram is trying to show is the drift in the guiding center of the oscillation as a result of this change in field. So is there a laser pointer on this? I think there is. Laser pointer. Yes, perfect. So if I start here, I'm in the weaker region. So I've got this nice big circle I'm going around here. And if the field stayed the same strength, I would continue to do a nice big circle back to where I started. But because I enter a stronger magnetic field, the radius gets smaller, and so I start doing a small circle. And if I stayed in the strong region, I would keep doing a small circle and back to where I started over here. Because I'm going between the two, we get this mismatch where I enter the weak field here again, and then start doing the larger radius, which then takes me over here somewhere. Then I'll do the small radius, which will take me about there. Then I'll do the big radius again, I'll be over here, and so on and so forth. So we do see a drift, in this case, towards the right, perpendicular to the gradient of your magnetic field, which is why this is known as grad B drift. We're really inventive with our names. Grad representing the upside down triangle for gradient. And we're too lazy to say gradient B drift, apparently. How you work it out? That's the velocity of your guiding center. I'd rather not do the maths in great detail. If you're interested in this, get yourself a textbook and spend hours and hours doing vector calculus. It's delightful. It really is. Okay, so that's one type of inhomogeneous B field. What if I change the direction I'm looking at my field and I now have one looking like this? So in this case, my field lines are curved, which means on the outside of the curve it's weaker because the field lines are slightly further apart, and it's stronger on the inside. A particle, or the guiding center of my particle, will follow the magnetic field lines. It likes to go around in circles around them. But if my field line is curved, the particle experiences centrifugal force. Centrifugal force is a sore subject for me personally. I dislike the fact that it technically exists, and that depending on who you speak to, they will either go, yes, absolutely exists, it's a very real thing, and we need to take it seriously, or they will deny its existence in its entirety. You probably will experience that, particularly if you did A-level physics, with your physics teacher drilling into you, do not talk about centrifugal force at all, never. But we do, in this case, we consider it. Centrifugal force is a force that points outwards as you go around a circle. It's why you feel like you're going to fall off a roundabout if you spin it too quickly. In this case, this is the centrifugal force. Again, nasty mess. I'm showing you this map so you've seen it, not so because I expect you to be able to do it. And any external force will cause your guiding center to drift. And this is known as curvature drift because your field lines are curved. And this is how you work it out. It's also kind of curvature. You've got a cross product with a gradient. So if you're a mathsy physics person, that will be exciting, probably. Yes. However, it's more useful to think of these two things together. We don't consider them separately. We just have magnetic drift, which is represented like that. Yes. So when you've got a stronger field on one side and a weaker on the other, it's not because, well, it's because you're going around a circle, right? But the property of having your field lines in a circle intrinsically means that it's stronger on the inside and weaker on the outside. So it's not necessarily the centrifugal force is caused by the stronger field and the weaker field. It's you're going in a circle, so you have a centrifugal force. Technically is, we just try to ignore it. It is a good question. I don't have a concrete answer for you because I no longer work in plasma physics. My gut instinct would be that the individual particle motions we're talking about individual particles, which are very small and therefore have small mass. And so any centrifugal force that does exist is going to be small. Whereas this sort of drift is we're thinking about bulk plasma. And that's why your mass is much higher, the force is more significant. Don't quote me on that. That's where I would start my search if I was going to try and find an answer. If you give me a week, I might be able to figure it out, but not today. Sorry, let me admit more people. Okay, right. Any other questions, actually, whilst we're taking them? Online, any questions? I don't know if I can actually see the chat based on... Oh, now I can. Okay. Cool, great. Let's keep on going. So, magnetic drift. Yeah, we rarely consider them separately because the equations are kind of too similar to ignore. We combine them into one big equation, which is called magnetic drift, which is just the two equations I showed you before combined, but with the parallel component of velocity and perpendicular component of velocity written separately. So that's parallel and perpendicular to your magnetic field lines, just to be clear on that. The properties of magnetic drift, which is probably the bit you care about if you don't want to sit and do loads of maths. It's always perpendicular to your magnetic field lines. It only depends on the gradient of your magnetic field that is perpendicular to your field lines. And it is charge dependent, which means ions and electrons will drift in opposite directions, leading to charge separation, which can be a problem because your plasma is supposed to be quasi-neutral, and if your charges start drifting, that's not good. And last but not least, on the whole, it's not dependent on mass, unlike other drifts we talked about already. Okay, so I just said that this force only depends on the gradient of V perpendicular to the field lines. What happens if the gradient is parallel to your field lines? So you have a weaker field going through a stronger field in the same direction the field lines are flowing. Well, in this case, it's a little bit similar to your polarization drift in that as you enter a stronger field, your radius of oscillation decreases, which you can kind of see on the figure there. Here comes some maths, and I will say this is the most maths we're going to do. This is the parallel velocity to the magnetic field lines, and it is equal to your combined velocity times 1 minus your magnetic field at the point in space you are interested in, divided by the kind of original magnetic field before you have the gradient, times sine squared of alpha. What is alpha, I hear you say? It's a little bit of trigonometry. I can split my velocity into its parallel and perpendicular components to my plasma. Sine alpha is just the perpendicular component over the initial to get the parallel side. Hopefully that's not too groundbreaking. But what if V over V naught sine squared alpha is bigger than 1? Anybody feeling brave with their maths today and can tell me what happens? Totally fine if you get it totally wrong. I'm not expecting anyone to know any of this. Any brave guesses? Maybe not. It's all right. I will put you out of your misery if you so wish. Oh no, is that a chat notification? I can't tell. I'm just I hate dual monitors. Where's my cursor gone? There it is. I've actually lost my cursor. Why is it on that screen and not this one? Oh no, I found it again. Okay, yes, person who's put there. Daniel, please enlighten us.
Would there be a negative velocity
Yes,
change?
Sorry, I've got to say that again for everybody else who's not in the room, not online. Daniel very correctly said that your velocity squared becomes negative. This is not good because we can't really have imaginary velocities. Maths likes it. Physics really doesn't. So how does this translate into the real world? It means the particle must be reflected when B equals B naught over sine squared alpha. This principle, this means that particles with too low a parallel velocity end up trapped in the weaker fields because they get bounced back. And this is known as the magnetic mirror effect. You may have heard of magnetic mirrors. And if you're interested, the particular force that causes them to bounce back is equal to the magnetic moment of your scenario, and then the gradient of the parallel magnetic field lines. That just means we only care about the gradient that is parallel to the field lines and not the perpendicular bit. Whatever happens in the perpendicular direction doesn't apply to this. So, time to wake you all up. Why don't we use magnetic mirrors for fusion? And I have another Menti, so it's exactly the same Menti as it was before. I've got to make sure that I don't leave people online out. So back to presenting this. I've got to go backwards because for some reason it's question 2. There we go. Yeah, particles leak. Any other suggestions? Trying to get people online. Can you see my screen? That's not the slide. Yes. Okay, great. Thank you. Yeah, I've got to swap screens again. What's that on? Yeah. Hi. Oh, have I broken it? Cool. Hopefully that is still working. Please tell me if it's not. Time actually. Oh, we're doing great for time. Too much money. Yes, we've got some good ideas coming through here. There is no singular answer to this, really. You're all right in a way. The big one is particles leaking here, I would say. That's the one that comes to mind. Yeah, we need high kinetic energy particles for fusion, which means they can't be trapped by magnetic mirrors because you need stupidly big magnetic gradients to get that to work. And even then, the highest energy ones, would you want to keep, escape, which kind of makes the whole thing totally redundant, makes your plasma inefficient. It's very, very dangerous. I don't know how dangerous it is. I know we don't build very many of them. Plasma drag, yeah, these are all good. But yeah, on the whole, you know what? I'm actually pretty impressed. How many of you knew what a magnetic mirror was before today? At least no one's going to admit it. Okay, fair enough. How do I stop? Oh, for goodness sake, stop. Nothing makes you feel older, right, than failing at using technology. So yeah, back to my slide. So we don't use magnetic mirrors, but we do use these two other concepts. So on the right-hand side is a tokamak, originally a Russian acronym that you've probably heard of before, and bottom left is a stellarator, which is kind of a tokamak's uglier cousin. The interesting thing here is you look at a magnetic mirror and go, yeah, that's rubbish fusion, don't use it. Both of these are magnetic mirror machines as well. Tokamak is probably easier to think about because the magnetic field lines aren't twisty and horrible and disgusting. But the inside, we get lots of, because your magnetic field is curved, going around this donut shape in a tokamak, the inside field is stronger than the outside field. So they are using magnetic mirror principles to try and trap particles in the middle. How do they get around the particle leak? Any ideas? Because effectively, some of the magnetic fields look very, very similar to the magnetic mirror machine. Go on. Yeah, they keep it moving in a circle. So they do lose the particles, but they lose them on one end, which is joined to the back end. So it just goes around in a circle, which means you don't lose your particles, which is great. The only problem is you lose them in different ways, which I'm not going to go into today because I'd need another entire presentation to talk about it, and my brain hurts as it is. Stellarators also have a similar principle, but they go off the idea of if I make my magnetic field super twisty, I get better plasma stability. But again, you don't get any plasma leakage from magnetic mirror effects because you're in a circle. Those things scare me, in all honesty. I have no idea how anyone plans to manufacture one of those, but that's a question for a different lecture. But yeah, actually, that's gone really well to time. I'm so proud of myself. So just to summarize, these are the defining features of the plasma. They have to be quasi-neutral, they have to be able to shield electric fields, behave as a fluid, it's described by MHD, and must have a large number of particles in their Debye sphere. I don't think I mentioned, the Debye sphere is just a sphere that has the Debye length as its radius. We're basically just saying you have to have something that is not only bigger than your Debye length, it also has to have stuff in the middle. Because if you don't have stuff, you don't have anything. You don't have a plasma, it's just a vacuum, it's very boring. So it might seem like common sense, but physics loves over-defining things. There are also lots of different types of particle drift. The ones we've gone through today were E cross B, polarization, and grad B and curvature drift, which can be combined to be magnetic drift. So on the whole, that's me done. I'm happy to take any questions. Doesn't have to be plasma physics, I will do my best. I do have a Google form feedback if you wouldn't mind filling it out. No personal information or anything, just kind of what you found good about today, what didn't work as well for you, just so that going forwards we can make necessary changes, if that would be good. But yeah, otherwise, that's me.
Difference between the all those other stars.
Yeah, this is not the Google form, not the societies. It's, yeah, just about today.
Can put the attendance on after that. So if you did the attendance on last week, you don't need to, it's just so we know who's coming to this thing.
I've got chats. What does the chat say?
A couple of questions.
Is this the only lecture of plasma physics? That is a good question. It's the only one that is planned. There is a lot more plasma physics that can be talked about. This was kind of the basics today. So if there's demand for it and you want to know more plasma physics, I can try my best. But at the minute, this is the only one we have. Is plasma really the only way to get nuclear fusion? That's a good question. You kind of inadvertently end up in a plasma regardless because you just get so hot that you transcend gas as a state of matter. I think even the ICF concepts that aren't trying to contain a plasma still produce a plasma when they use an explosive shot. So as far as I'm aware, you can't do it without a plasma, but I think it's a byproduct rather than a we intend to make a plasma and we have to have a plasma to have fusion. No love for cold fusion or astral system. Yeah, okay, you've got a point. Yeah. I'm nowhere near an expert on cold fusion. I need to do a lot more reading of that.
Any more questions, guys?
What's cold fusion? Yeah, that's a very good question. I'm not qualified to answer that question. I'm going to hang around for a bit anyway, so if you don't want to ask a question in front of anybody else, I respect it. I would never have wanted to do that. You know, I'm not going to hold you hostage. If you want to leave, you may. If you need the attendance QR, come and see one of us and we can give it to you.
Well, we've got your day.
Can I see the summary slide again? Yes, you can see the summary slide. In fact, I think we're planning, this is being recorded, so I think we're uploading the recording anyway. Give me a minute, I can't get my cursor on the right monitor.
It's less like more about the room size.
There's a summary slide for those requesting it.
Yeah, we can look at getting bigger rooms because we're more comfortable. Is the engineering list everyone? Because I don't want to go into the lecture yet with their people. I'm trying to look at bigger rooms. One of the meeting rooms down there, so will be fine. And the other thing is, will people be up for not less weeks, but in future things social after these lectures, or is that not?
What materials do we use to hold plasma and why? We don't, is the answer. If a plasma touches a material, most of the time it melts it. The idea is to not have them touch magnets for MCF and just explosions at ICF. There is going to be electron materials for fusion, so that you may get your question answered then. Does the physics change for different machines? Yes. I don't know the specifics for each, but there is a reason why the plasma for a tokamak has as many magnets as it does. Why accelerators have many more in complex shapes. I'm not an expert on designing magnets for holding plasmas. I suspect they're not going to spend more money on making magnets that they don't need to make. So there will have been some simulations done that proves that the magnetic fields that you're producing with your magnets is enough to get the plasma to do what you want. And if it's not, well, you've got a machine that doesn't work how you wanted it to. So that's not ideal. Sometimes as well, they make more magnets than they need to have spares. But I don't think that's very common. It can help you. It's not. Right, people argue about it quite a lot. You start looking at condensed matter physics to tell you. Sorry, yes.
All the particle in the magnetic field. Magnetic field is like this. I use the right hand, but actually it's the same. Then we have the
Okay, that one, yeah?
no, I mean the 3D one.
Oh, the 3D one.
Yeah.
This one?
Yeah, this one.
Yeah.
Yeah.
So your magnetic field is pointing this way. Your charge path, you have to kind of pick a point, right?
Yeah.
So if we take where the positive charge currently is, it's moving into the page. So I have to kind of break this.
Yes,
Which means the force is acting downwards.
I think that, and it's like this, and I know that, but it's also like moving to the right. So it's like
Yeah, it's also
this.
moving towards the right, and you are right that that will have an impact.
So that's like Never mind. No. Yeah.
But only the component of the velocity perpendicular to the field
perpendicular.
line.
So, and what about the tokamak one? Yeah.
Yeah, keep going, keep going.
Oh, this one.
Yeah, this one.
So which one is like, so magnetic field is like
So
there.
this one is different because the force isn't coming from the magnetic field itself, it's coming from the change in the magnetic field, like the gradient of it. Because like we're moving kind of in the same direction as our field is traveling. So yeah, this is a particular force where it is caused by the gradient of the magnetic field, not the magnetic field itself.
Okay.
So that was a bit of an odd one out.
That's
And you wanted to look at the
so
top.
what does like this one? What is this one's called?
This is called the magnetic mirror force. Oh no, sorry. Hang on. Yeah, so
So the magnetic
the
mirror.
force that is created as a result of this is called magnetic mirror force.
Yeah. Okay. But like this one is like it's why
Yeah.
is like
So you have circles because you have magnetic fields.
yeah, but like this velocity is pointing. Oh, it's pointing out.
Yeah, this
Oh,
one's
yeah.
kind of coming
Oh,
out of the
okay,
field because they're
okay.
trying to represent
Yeah.
a 3D picture
Okay.
with a 2D diagram.
Okay, so this one is the magnetic field. So they come to this end because
So
the
magnetic
gradient
field
is
lines
turned
are
back.
the green lines,
Yeah.
and you've got the strong field at the ends and the weak field in the middle.
Okay, so
So
okay,
your particles keep bouncing from end to end and then trapped in the middle, but your fast ones escape out the ends.
so why they are like from the start? Why they are like
Why they gyrate like
yeah?
that?
Why they do?
That's because just because of that.
Oh.
Anytime there is a magnetic field, if it's moving perpendicular to the field, it will start making circles around the field.
So at the start of the point, it is like it has a like perpendicular velocity.
Yeah, so
Yeah.
it's not making circles. Because these are these ions that have some sort of thermal energy now.
Oh, yeah.
I like all of you.
Get it. Thank you. Yeah.
No worries. Okay, who's next?
Charlotte, so my name is Max. I'm with the Debye Party Fifth Society.
Lovely
I think
to meet you.
Imran or Tom mentioned to you that it's going to ask you about doing some talk
Yes,
sometime next week.
sometimes next
So-
week. I can't do Tuesday or Wednesday.
So end of
End of next week.
around this time.
Hold on. Sorry, my diary's a mess. Yeah, this time on Thursday is fine.
So basically, the idea would be maybe we could do some kind of seminar Q&A, and you could do a condensed version of this
Yeah, which
presentation.
parts you? I'm guessing you don't want the basics of electromagnetism because if you're the physics society,
No,
you're
exactly.
probably
I think
gonna
we'd
love it.
be particularly interested in the more.
I can dig out the maths.
I'm sure.
I deliberately didn't put it into this.
Yeah. In fact, I did have a couple of questions. One was on slide 22.
Yeah.
It's still the same. but we have-
I just thought there's more that could be added mathematics.
Yeah.
Okay, this was, where we had the imaginary.
Yeah, and why is it?
Yeah, could that be explained in terms of phase shift, basically? And
think
can
it
that
can.
be expanded
I
on?
will need to go consult my
No,
notes.
not just my instinct, I don't really
It's
know.
mine too.
And then the other was on that slide 20. I had a moment.
20. You're so good at keeping the slide numbers. I'm terrible. This one?
I knew I would forget. Right, it says it's not dependent on mass, but the cyclotron frequency, is
Oh,
Cooper.
sorry, no, it is.
So it must be dependent on mass, no? Proportional to it, directly.
There is definitely a reason why it's not. But where is it?
I mean, perhaps the velocity squared themselves, that's the mass dependence, which I forgot
Might
about.
do. Very good question.
Because you said this one does have a mass.
The centrifugal force does.
No,
but
sorry,
because
not
it-
the force, I mean the velocity that you wrote beneath this centrifugal force.
So I think this is because F is like NA. And
Yeah, that is
Right,
FELMA.
it will drop
Right,
out.
that's where it drops out. As to why
maybe.
This is because I think derivation.
I mean, you wouldn't.
Not derivation. You integral to the acceleration and you got
Yeah, you wouldn't expect the velocity to have
Yeah,
mass dependent
you're right.
because it's units. I don't know. I just heard it, and maybe I misheard something.
No,
But I just
I think you've got a point. I've got this from higher authority. I am not a class of physicist as my day job. I'm going to have to I'll have another look before next week.
Okay.
And if I can give you a better answer, I will.
Yeah, if you'd like to have it, just
Yeah, sure.
let me know. But otherwise, I'm very happy if we just sort of
So same
this with our
session.
society, just saying,
Yeah.
yeah, it'll be up to an hour to ask questions, hear a bit about part of physics.
Do you want me to cut down on the fusion bit slightly?
I thought it was really interesting when you had the fusion diagrams and
the end.
what's the fusion bit.
Well, the fusion bit is basically just how does this apply to fusion?
No, I would really like to.
You
see that.
definitely want this.
Yeah, I think that's interesting. I think it expands what people know who are coming to us. Like it's covered a lot of the EM stuff, I think, but not the gradient expression.
Yeah.
And they won't know the application.
Generally do that stuff because it gets nasty and kind of messy, and your average person is not going to need that realistically in any job they do, unless you do this.
Because you study theoretical physics.
I did it at Durham.
I think you'll know best than I do what sort of steps.
Okay, that's fine. I can do that for you.
Let me know if you have any. Thank you.
What was your name?
Max.
Max. So
Yeah.
I'm just going to make a note because otherwise I will forget.
Yeah, and in on to you can get in touch with me at any time.
Oh yeah. Okay. Thank you. Okay, right. Who's next?
Zach, firstly, this is sorry again.
Don't worry, we've all been.
I just a few questions, mainly for Matt. In the Debye showing here, what do Z and
Oh yeah, that's a good point. So Z is your word, like charge number. Effectively, what I'm trying to do here is Q times your electrical flux. So Z times E is what the charge will have. So if it's an electron, Z is 1. But if it's a helium ion, it's Z is 2.
But all the
All of them is electric potential energy equals like when they're about equal, yeah.
what? I don't really have answered one question.
Yeah.
Yeah.
So if you're doing a physics degree, you will do graph, curl, yeah.
A lot of it was covered in A level, and I thought I was keeping up with my 7 level.
Don't worry, your first year is trying to figure out where the gaps are and figure like do it whilst the exams aren't just high pressured.
I mean, these first set exams I have in January account to like 1.7, 5 grade.
They're effectively it's easy to get
Or magnetic mirrors. I got lost at the end. Why would you want that, or would you not want that? Or is it just a cool thing?
So when fusion research was starting, it was mid 20th century. Normally with the Russians and Americans, it was kind of Cold War times. They were both trying to do fusion because they realised that we could do but the first concepts were magnetic mirrors because they realised with these geometries you could confine particles. Whereas before it would be great, I can make a plasma, but it immediately goes off in all directions, hits things, melts things. So this was kind of first go, and they realised that they have loads of plasma instabilities associated with them, but also that they have like particle leakage. You're losing energy particles if you want to keep, which is rubbish of fusion. And hence the tokamak kind of came out of it with a, well, what if we join the ends up? So you don't have that problem anymore. You just create a couple of others. I won't bore you with the details right now because there's the discussion to be had there. And I think Tom's covering it in a different lecture as to what is the tokamak and what is its why
We reviewed top of that last.
Yeah, I think you've got a dedicated, like, machines lecture. I would have to check, but I think it's.
Confirmed.
Yeah, no worries.
We see you again.
I think lecture on superconductors at some point. But that's not the one. But otherwise, I'll be around. My research is in fusion.
So what are you doing right now?
I'm trying to make answer or figure out how we can make things out. It's not as easy as it sounds. It's, yeah. I love my job and I hate it.
I think that's most people.
Yeah, tungsten's just really, really brittle. So I'm coming up with a kind of a welding between it. How on earth we want to build these giant reactors? You know, people saying let's build the first one. Let's build the kind of right. And kind of fumbling my way through it. Nobody has a really large scale machine. It's been probably tested out. It worries me. It worries me deeply, but no one else seems to be worried about it. So, yeah. They'll worry about it one day, probably when it's too late. They go, wait, I was working on this. I was like, yeah, I was. And yeah. That's side. Like fusion has a tendency to be a bit temporary. They will say whatever, particularly in the private office, they'll say whatever they have to say to get on. So anytime a private company comes out of announcements, people
Yes, I know last week we were told that sort of they've changed the name of fusion.
yeah, so is it fusion? Is it nuclear fusion? Or it really does. It starts veering into politics. That's not fine. Say that. Yeah, I mean, someone's got to do politics on it. I'm not going to be like. But yeah, thank you for your interest.
Very interesting stuff.
Yeah, like I didn't have anything like this when I was undergrad. They're under the redo fusion. It does good at magnets. Really do. Even though it tested magnets for either. There's like one research group that was. My old supervisor who's left the university now, I did the neutronics that I use. Yeah, it's I'm just quite fun, but he's not.
What's a new
Oh,
just
and you can get like you're looking at the neutrons that come off your they you can actually have a lot of stuff on the neutrons the way they are. That takes you back. It's interesting because you can't stick them on. Something. Neutrons is one of them. They try different things. I have quite a few friends and colleagues who work on that. She adds an extra magnetic field to see what the plasma does and how that produces another magnetic field, and then that's that magnetic field, and that helps. At that point, I get it. Yeah, so it's very comfortable. Lots of people make sure I'm pretty cool. Like cigarette. Yeah, I think is anyone actually still here? No, it's just me. Right, bye everyone.